Okay, I think we are live. Hello everyone, welcome back to nMage, where we build a full game engine, hopefully complete one, fast and go from scratch, minimal libraries. Um, I hope everyone enjoyed the break on the holidays, so we took a small hiatus, and now we are starting episode 10 actually, day 10, which is kind of amazing that we have gone um, all this time. Already, I think we're about 20 hours of work done, streamed live, and actually more behind the scenes because we did need a math library and we needed some kind of asset importer. So we're using assemp from C++, supported to go already. And now, today, I thought it would be nice to kind of ease into the flow and also take a small break from doing all the graphics work with OpenGL. So we can tackle and look into timing and delta time and all these concepts because they're extremely important and very easy to get wrong as well. But they don't need any kind of external libraries or any kind of complex system like OpenGL to do. They're rather simple, but we do need to get them right. And then we'll be able to do like FPS counters and things like that. So let's get going. Maybe, I don't know how long this will be, but hopefully not too long a stream. And then next time, I guess, we'll go on continuing with graphics. All right. So I want to start with, and of course, here is our nice little screen with lighting and kind of weird movements that we have. But yeah, I wanted to discuss first, what do we mean by timing, why it matters, what's delta time and all these things. And if you have used Unity or other game engines, even any game engine really, you might have seen these. You probably interacted with those. So let's discuss them before implementing them. So let's get Milton. Okay. So let's imagine we have a game and let's say we have a cube and the cube is moving in this direction. Maybe let's say it has a speed of 1, right? Or let's say it's a speed of 2. So I'm not defining units here. That's what we're getting to, but let's say it's moving 2 units, maybe 2 meters or something, every frame, right? Because the game runs in frames. We update the logic, the position, we draw the graphics every frame. So this cube here is going to move. So here, let's say frame 1 by frame 2, maybe it's at this position, right? And so the distance between these is 2. 2 whatever, right? Whatever is defined in the game engine. So for example, in Unity, it says unit of 1 is 1 meter, more or less. So if you have a cube of 1, 1, 1, that's the default cube. So it's 1 meter by 1 meter by 1 meter, right? So that's kind of the movement rate. Now, let's say we have a wall as well. And the cube, so we have physics that has to resolve. And the cube is going to move maybe this distance is only 1 meter. So it's 1 meter away. So at frame 3, kind of up. So at frame 3, what's going to happen is the cube is going to be around halfway inside the wall. And then if you have a physics system, a collision system, it's going to detect that there has been an intersection between these two bodies, and then it's going to push the cube back. Now, if the cube instead is moving faster than 2, so in this case, let's say it's moving at 5 units. what's going to happen is at frame 3, it's not going to be intersecting, it would have already passed the wall. And this is not really a nice cube, but it would have already passed the wall, right? And depending on your settings and how your collision works, this might not be detected as a collision. What should happen is, yes, theoretically, if we ignore the wall, it should be there, but since we have a physics system in place and there is a wall in front of it, it should actually collide at this point. Now, is this detected? Is it detected that this has passed an object it should have collided with and the result? That depends. If you have continuous collision, which is slower, but takes care of these things where it looks kind of where it was and where it is now, it would detect. But if we are only checking where it is now and we ignore where it was, then this will not be detected because we'll check, okay, there's nothing touching it, so all is good. Now, going back from collision a bit, this kind of very standard movement step, and that's why sometimes in games, if you're moving too fast, you might clip through things. And this clipping where you're moving really fast and you kind of ignore the wall and cross the wall, that's exactly what's happening. You're moving at such a speed that between one frame and the next frame, you're jumping over things. You're jumping over walls and objects. But usually the frame rate is high enough and the speed is low enough that this doesn't happen in most cases. Now, why does this matter, right? Thing is, we say frame and frame, and each frame we're moving 2 meters. Well, in the real world, and ignoring relativity, time passes, right, at a constant rate, more or less, for everyone. If 1 second passes for me, someone else on Earth would have also 1 second. So when we calculate, for example, the speed of a car, we'll say some meters or kilometers or miles per hour or per second, we can convert it, right? And so we know if I say my car has a speed of 5 kilometers per hour, hour has a specific definition. Now, the problem is in games, if I say I want my object to be moving, in this case, let's say 2 meters per second, 2 units per second, whatever this m is, I want it to be moving at speed of 2. That means from frame to frame to frame, I'm expecting that every frame I'm moving the correct amount. The issue is frames are not constant. While time passes constant, like at a constant rate in the real world, that does not happen in games. So the distance or the time it took in actual real time, or the how long the computer took, let's say, between one frame and the next varies. So let's say at this frame, between these 2 frames, maybe it took, for example, let's say the computer took 0.1 seconds to process all of this. But perhaps, we had a big explosion and then this frame to this frame took 0.5 seconds. So now it moved for the same amount of time, for a different amount of time, it moved the same distance, which is wrong. If more time has elapsed, then it should have moved more units, right? Excuse me. Shut this off. Right. So if I'm crossing the same distance, 2 meters, in 0.5 seconds instead, that means I have gone slower. And all of this, really, if we're really saying seconds, then what's the unit here? It's not 2 meters per second, it's 2 meters per frame, okay, but then the frame should take the same amount of time. And what I'm getting to is we want something that helps us ignore these differences, or at least adjust for these differences in the timing between frames. If you play a game, you're going to see your frame rate as maybe 60 frames, and then it's going to drop to like 50, and then it's going to be maybe 60 again, and then it might drop to 55, and so on. While all that happens, the physics in the game doesn't change. The way the game behaves doesn't change, and that's because the frame times are being accounted for. At 60 frames per second, the time between frame 1 and frame 2 is around 16 milliseconds. It's around that. And at 30 frames per second, the time between one frame to another is around 33. And then at each, so every time the frame rate changes, they have different times between frames. So we need to handle these in such a way that our objects in the game move at a constant rate. If their speed is 2, it should move at 2. So how do we do this? Well, the idea is we want, what we have here is movement per frame. That's really what we have. From moving at speed of 2, and it's being done every frame. So I have 2, let's say, meters per frame. Perfect. What we want to do is convert this into 2 meters per second. So it doesn't care about what the frame rate is. It cares about the speed we are trying to simulate, regardless of if the frame took longer because my computer has some other program running, or it was faster because maybe this frame we're looking at the ground. There is nothing to render. There is a lot less work to do. So the frame took a shorter amount of time. Still, the object should not move faster. And that's actually a bug in some games. And if you guys have played Skyrim with mods, if you push Skyrim to, I think, above 60 frames per second, it starts speeding up. The whole game speeds up because these things are not accounted for. So how are we going to do this? Well, it turns out to be relatively simple. All we have to do to get per second movement per second is to keep track of the time it takes between frames. So let me just clean all this. Here. Right. So between this frame, we're going to get a timestamp. So let's say we have T1, we have T2. We keep track of when the last frame started, right? And when it ended, T2, and the ending of frame 1 is the start of frame 2. So when this started and when this ended, if we do, we can get something called the delta time, or just dt for short, delta time, equal to T2 minus T1. That's all we do. Delta time is the time it took the engine to process one frame. So running the physics, running the logic, and the rendering, all of that. How long did it take us to do all of this one time? So for frame 1, how long from the start of frame 1 till the end of frame 1? Or how long from the start of frame 1 till the start of frame 2? Same thing, right? So we subtract the 2 times, so we get kind of a timestamp. Let's say now maybe it's around 8 p.m. So let's say at 8 p.m. 8:00, and then let's say our thing is really slow. Let's say at 8:02. So that's the start of the frame 1, and that's the start of frame 2. If that was the case, then we just subtract this time from this time, and we would know that the frame took 2 minutes, which obviously for us, it's not going to be in minutes, it's going to be in milliseconds. That's the usual time that we have. Now, so, okay, we know what the difference, or delta, stands for difference if you're not used to the terminology. So delta, what's the delta time? Now we can take the delta time and we can multiply it by the speed. So we have a speed that we want, like 2. Instead of saying of moving the object by 2 units, what we're going to do is we're going to move it by 2 units multiplied by the delta time. Now, why is that? Well, let's think about it. If processing the frame takes a second, then we just have the speed. So from frame 1 took 1 second, so we're multiplying 2 by 1, and that's just 2. So we have essentially our speed in, for example, meters per second. That's exactly what we want. Okay, what if the frame took shorter? So if the frame took 0.5 seconds, well, when we multiply 2 by 0.5, it gives us 1 meter. And that's again correct. That's what we expect to happen in the real world. If I'm moving at a speed of 2 meters per second, but only half a second passed, then half the distance should be moved. On the other hand, if our delta time is 2 seconds, then it should be 2 by 2, which gives us, 4 meters, right? Again, that's what we expect. This is what would happen in the real world. By keeping track of delta time and multiplying anything that has anything that has to do with timing or movement, we adjust it. We move it from being frame based to being second based. So instead of everything originally being 2 meters per frame, this multiplication converts it to be 2 meters per second. Because as we saw, if we move it proportional to how much time was spent. That's also one of the reasons where if your computer is really slow, and I don't know if some of you guys have experienced this, but if you have a really low frame rate, you would see things maybe jump. If you're in a car, then one frame is here and the other frame, it has gone a long distance. That's because your frame time is really low, is really big. This dt is huge. You're maybe taking about a second to process one frame. So all these numbers are being scaled up, and then your objects seem to move a lot further. On the other hand, normally our delta time is really, really small. So at 60 frames per second, it's only 16 milliseconds. So this thing is very small. So we see things move very smoothly. We don't see jumps like, oh, I was here and then I jumped to this position. No, it's here and then it would be sort of blue. Maybe next frame, it would be here. So there is a tiny amount of movement. So the speed might be 2 meters per second, but we have only moved this tiny amount because our delta time is so small. So it makes movement proportional. Now, what we need is kind of built-in way into the engine to keep track of the time since the game started, since the engine started, and to give us accurate timing and delta time information. Most of what you use usually is delta time, but you might also want to know, like, okay, what's the current time, or how much time since the level loaded or the game started, things like that. Right? So, if you guys have any questions, please feel free, tell me. But let's start code. So, I think let's go and make a new package, something like timing. Yeah, because the Go standard library already has something called time. So let's do timing. Package timing. Oh, this is clear enough for everyone. Okay. So let's see. So the timing, the place we want to know is this is all initial. It's really the game loop. So in here, we need to track starting time, and then we can remove this track end time, right? So here we need to tell the timing package that a frame has started, and here we can tell it, or we need to tell it, the frame ended, and it should be able to provide us with variables of what's happening. All right, let's do then in that case maybe frame started, just kind of callbacks. Frame started and frame ended. Let's see. So we need some variables. One is for sure the dt, delta time, which is float. I think float 32 is good enough. And let's see. And we might want to initialize it to something very small, just so we don't end up, if someone uses it at startup, we don't want to give them a 0 just in case they are dividing or doing something like that, and then it gets an error. All right, that's the delta time. Probably want last frame, or just frame start, frame. So at frame started, we can say frame start equals time dot now. And this is probably not that accurate, but let's see. Okay, let's do this. Time dot time. And then frame ended, and we want to calculate the time it took since the frame started. So we can do time dot since. All it does is it does subtraction from time dot now, which is the time at the frame end, minus sub time t. So you can say time dot since frame start. And this thing is basically our delta time. So our dt, let's see, should we get milliseconds or microseconds? I think microseconds is too much. Yeah, I mean, we can provide a 64-bit delta as well, but that will be the default, I think. So yeah, milliseconds. Cool. So we don't need frame end. And dt, we can either make it a variable that's public, or we can make it a function. What do you guys think? Well, I think it's okay to make it a variable. That someone could change it. Well, let's do a function. Gives back 1232 dt. If it's annoying, we can change it. But I think that's it. That's about it. So in here we can call as usual. Okay, takes a bit. This code is kind of slow. No, here we fire frame started, and here we can do frame ended. We don't need delay anymore. Well, we didn't need it before as well. One thing we can do is now every frame we can set the title. So set title. fmt.printf. What do you want to print? Maybe FPS. And delta time. So FPS is what? That's not necessarily the best way, to calculate it because you might want to average it over a few frames. But for now, one way is the delta time can be converted to FPS by just converting it to seconds, I think. Um, let's see. So first, let's get timing, delta time, and just see the delta time makes sense, and then we can do the FPS. Okay, so this is really small. 10. Okay, 10 10 milliseconds. Is that right? And then FPS. All right. So for FPS, let's do, I think, so FPS is how many times is it going to run per second. So what we have is a time period, how long it took for one time. So probably we can just divide, if I'm not mistaken, if I got my math right. We can divide this and convert delta time, which is in milliseconds, into seconds by dividing by 1000. So this converts it into seconds, and then we get a frequency. It should give us FPS. For us, this should be really, really high. Let's see. Hundred FPS. Well, to check our math, what we can do, get our calculator. So at 16 milliseconds, we should have around 60 FPS. So we can divide 1 divided by 0.016, and that gives us 62 frames per second. That's correct. So just by dividing 1 over this thing is enough, and we don't need the brackets. So 1 divided by delta time, and these, yeah. Divide this, divide by 1000 to make it in. Yep, I think that's it. And maybe a comment would be nice to say T is delta frame delta time in milliseconds. Okay, the calculation broke. Why is that? Already a back to it's one thing is 100 FPS seems slow. Yeah, 100 or so. That seems relatively small. Should be a lot higher. So first, let's just deal with this because it's annoying. We can say this is a floating number and we want 3 decimal places just so it doesn't keep shrinking, expanding, and shrinking. And then here we can say, I think, I don't remember actually, it's a decimal with, well, 5 digits, I guess, 6. Let's see. Okay, that's it. Oh, okay, it's a float. All right. Delta time, I think, shouldn't be a float. It's milliseconds. Yep. So we can cast. I mean, you can give the delta time in seconds, so no one has to divide themselves. Yeah, I think that would be better actually. So we can just do that's seconds. Yep. And that gives us a float 64 per. Yeah, that's better actually. That's more usual, let's say. Okay, so that's float, and that is a float. We can limit it to 3 digits. Doing this 1, 2. Actually, we don't want on the FPS. We don't want any digits. Can I just do 0? Okay. Delta time, yeah, delta time can have even 6. Yep, now it makes more sense. So our delta time is 0.01 seconds and is pretty consistent. And then FPS is hovering around 100 FPS. I am confused though by how slow it is. So maybe we can have kind of a small performance session, although that's, that's too soon for any performance talk now. We barely have an engine, but yeah, like I'm expecting this to be in the high hundreds at least. I don't know if OBS is affecting the performance, but well, so we have our FPS. Now, one thing, if we have any movement, let's see, we move the cube. So we only move the camera, but I guess, yeah, I mean, we don't have any speed stuff yet, so maybe later when we start setting up, yeah, when we start setting up kind of objects, I think that's one of the things I want to do soon. So now we have this is awesome. I want to move all the buffer stuff into a mesh class so you can have these things easy. UI, we can just move it. And then, yeah, I haven't decided an object system. We might want an entity component system, but I want to keep things simple now and just have something functional. I want to make a game with this as soon as possible. So probably we need to abstract the window class, get a mesh class, and then objects. Maybe some basic UI. Textures, if we're doing a really, really simple game, maybe we can hold on, wait. But yeah, guess that's for next time. I think that's it for today. Small short session. I think we're done with timing. Did I forget anything? I don't think so. Because in Go, it's really easy to get the current time, the actual time. Perhaps we want to get an engine start time. Might be useful. So let's have start time. And that's just the kind of time. And then let's say init, and in here we can do time.now. Then we can provide functionality where someone can ask for time, or what do we say? Start time? No. Elapsed time, maybe. We can call this for now, which gives us an int. Yeah, say an int, which is, or honestly, yeah, uint returns time.since, so the same thing. So how long has it been since we started? Start time dot seconds. That should be it. Now it depends when we want to call init to consider ourselves started, but I would say something that's fine is right about here. Here we can do timing dot init. That's fine. Actually, let's do elapsed. Timing dot elapsed. Let's add a comment. Time, then stream start. If this works, we're good to go. Your timing package. Yeah. So every second it increments by 1. That's exactly what we expect. 5, 6, 7. Yeah, it's correct. We have 100 frames a second. Again, I don't like the number, but guess we'll see. Okay, so thank you everyone for coming to today's stream. I think we stop here, and you all enjoy. Good night.